All right. Thank you so much. I really appreciate SecT. Thank you so much for having me. I hope we'll have a good time with this presentation, but welcome, and let's just dive into this because I've got a lot to say, and I never have enough time to say everything. Okay, so let's get into what to expect here. Okay, so a few things, hopefully throughout this presentation in which we're talking about malware analysis, binary analysis, and then how we can apply artificial intelligence to help us detect new malware that we've not seen before. Here's the overall structure for our presentation. And so I don't have like an exact live demo, but still things can always occur when we try and show things. So in case anything shuts down, I'll do my best to recover as best as possible. But just a quick disclaimer, at least the views and everything that we're talking about, they do not represent the views of the United States Air Force or the Department of Defense. It's just my personal research that I'm doing on behalf of my lab and my university to hopefully be useful to our cybersecurity community. Okay, so research motivation. Now, I have a couple of quotes here. One, we say any sufficient advanced technology is indistinguishable from magic. I really like that phrase because sometimes when we talk about artificial intelligence or machine learning, it seems like we're sprinkling magic on something and saying we're using the AI to do something. But overall, I'd like us to understand, like, how can we convert data from whatever we're looking at, how can we feed it into models to give us useful detections and useful decisions? And so that's what I'm trying to say here. The goal is just to demystify how we can apply artificial intelligence into our current research. Okay, did I go back? Okay, so one of the questions, yes. All right, so one of the questions that can be asked, because like we've been using artificial intelligence, machine learning for malware classification for a while. Now, some people might say, okay, let's address the elephant in the room first. So some will say, well, in our enterprise, in our environment, we have antivirus, we have SOCs, your Security Operations Center, we have compliance, we have next generation insert appliance here. This is sufficient in order to help us detect new malware of tomorrow. Well, that's possible, but I like to have a chart kind of to set the stage. And so VirusTotal, hopefully many of us, if you're at the conference, most of us are familiar, at least with who the entity VirusTotal. And so they have a dashboard, like every day, that they explain how many new malware samples that they have received. And so across an entire month, you can see like the overall trend of which malwares they are receiving, and then how many are new or distinct samples. So as of July, and even July going into August, August going into September, this number has constantly been increasing, in which they say per day, they receive over 2 million, on an average, over 2 million samples for analysis. And of those 2 million samples, 1 million, over a million, now we're at 1.8 million distinct samples are provided to VirusTotal daily. And so something to keep in the back of our mind is, okay, how often are our antivirus or our compliances that we have and use, how often are they updated in order to keep up with this trend of nearly 2 million unique samples that are created every single day? So overall, it's not an industry problem that we just need to buy some product. It's something that many of us can research, and we'll have to continue to always be researching in this area to hopefully stay ahead of the adversaries. And so this is something that I posit. I say we need new strategies in order to help us better detect malware of tomorrow. And I believe those new strategies lie in the incorporation of artificial intelligence, machine learning, and even natural language processing. Okay, so let's get into the formal problem description, or the formal problem definition. There are 4 main ones. That's kind of the overarching guide for the entire presentation and the research that I'm doing. Number 1, there lacks an overarching description of how we can take malware and binary samples apart, how we can analyze these samples statically, dynamically, and even extract artifacts from memory, and then have a uniform language that we can use to describe these samples. The second one, there lacks a robust framework that's able to automate this entire analysis pipeline. So again, we can get that aforementioned data set standardized in the right nomenclature that allows us now to pivot into artificial intelligence and machine learning modeling. Number 3, there also lacks a large updated malware analysis, like a data set or a benchmark that we can use to continuously adjust our models, evaluate our models, and make things better for the future. And so that's an important point, because if we do a literature review on like current people that are doing research in malware analysis, research in artificial intelligence, et cetera, something you'll constantly see is the data sets that they are using in order to evaluate their systems and their models are very old. Some data sets, even in research that I was analyzing as of just last year, 2023, they're using a malware benchmark that was created in 2010. And so malware has advanced since then, but we're still using data sets that are over 10, almost 15 years old. And so we need to constantly have a framework that can help us update this data so, again, we can make our models better. And then the last one, that also lacks an ensemble, a heterogeneous ensemble that's able to increase that detection and the precision with high accuracy. And so overall, overarching, this is what we are doing in our research in order to help the community. Okay, so something I'll mention many times is model. Model, model, model. What is a model? So we start with the model. Okay, so if we just define this quickly, a machine learning model, it learns patterns from data, and then it uses or creates a mathematical function that can help us make predictions. And so if we look at a supervised machine learning model, we can try and find a relationship between our given features and then the response variable. So let's look down here. In this case, let's say we have a linear function that we are analyzing. And so in a linear function, we want to understand the weights that are applied to each of our input variables in order to help us predict the dependent variable. And in the slides, I use this y hat, which is common nomenclature for us to discuss. This is our prediction of the function for the variables that are coming in. Because if we can understand this part, then we can see how to better apply these models to various data sets. Now, if we expand a little further, let's say that this is our input. So input here as a scatter plot. We can say this represents, let's just say it's years of children, like their children age development. And then here we want to understand what's the normal height that the child is supposed to be at a specific growth year. So we can look from history, we can look at historical data to understand and try and find that, we call it the best fit line, or a regression line that can help us understand, like these are my input variables coming in, and then if I can figure out the weights that are applied from our history, we can now use that to make decisions moving forward in the future. So overall, we're looking at data that we have, we analyze it, and then we try and find that best fit line. When we can do this time and time again, and then when our prediction is really close to what our ground truth should be, we now say our model generalizes to new unseen data in the future, and then hopefully we can trust that to help us make decisions moving forward. Okay. Now, let's talk about models to know. So if we're getting new, or if we're just getting started into this domain, I try and put a few to just start to be familiar with. So if we understand a few of these models, like learning and reading more of these in the future, it's actually much easier. And so when we talk about machine learning tasks, the two ones that we'll discuss today is supervised learning and unsupervised learning. So when we discuss supervised learning, we mean it as all of our data sets that's coming in, it's fully labeled. And by a label, it just means if I have different features that are coming, I also have a label or a classification, for instance, of what should the ground truth be. So again, I can learn from historical data, I can evaluate my model to the historical data, and then it can tell us if it generalizes. So if we can generalize, we say we can trust this model and use it to make new predictions on unseen data for the future. So under supervised learning, there are two main ones, classification and regression. So when we talk about classification, it's just we want our model to tell us if I give you a sample with a specified feature vector, like here's the size of the sample, here's code that we've seen inside the sample, here's what its imports look like, et cetera. Those are features to describe a sample, an instance. Then we want to determine, is this sample malicious? That's a classification, yes or no. Or does this sample belong to a specific malware family attribution? That's a classification. So on the previous slide, we spoke about a regression. So if I give you continuous data, I want to be able to predict where that, the future data or the future prediction, what that should look like. And so again, we can just research these. There are very many YouTube videos that can help us see how do we apply these different models given the data in order to help us make predictions. That's supervised learning. Then unsupervised learning, we don't really have a label or a prediction. We don't know what the data should be. We're just analyzing to see, okay, what are some of the trends? What are some of the associations, some of the clustering that the data can help us provide? And so there's no time in our presentation to talk about unsupervised learning, but yeah, your two main ones that we'd care about is clustering, as I said, like an association, or some dimensionality reduction if we just want to reduce from a higher dimension space to a lower dimension space to keep our models as simple as possible to help us make the better predictions moving forward. Okay, now let's get into our machine learning workflow. And so I put this workflow together kind of as a general guide towards, okay, how do we now start to get closer to applying this analysis approach to help us make predictions? So the first thing we always start with some sort of understanding. In the literature is referred to as business understanding. And so then the business understanding is just when we have some data that we want to go after, or we have some data that we want to analyze, and now we start to see what do we want to extract in the data. So again, we're working on malware classification, so if I have many malicious samples, one of the things I want to extract are the appropriate features to help us classify the data set. So we just know, like, what might we have, and then what do we want to do? We start to form also some hypotheses that can help guide our research. Then we go towards the data collection. So the data collection, if you're lucky, you have structured data, which makes it easier to feed into the models. In the real world, the data is it's noisy, it's messy. And so now we have to use some code to try and clean it and convert it into an appropriate structure so we can begin our analysis. So we gather, we have some area where our data comes from, then we move towards our data wrangling. So data wrangling, other literature will refer to this as data pre-processing, and that's just where we have some data that we've procured, and then we do some exploratory analysis. We may refer to this as EDA, exploratory data analysis. Now we're trying to figure out what are some general trends in the data. So if we know the trends in the data, we might be able to already start to identify what specific features might we want to feed into our models. Then we go towards some augmentation. I might want to add some features together or do various functions, and I'm cleaning the data set in order to get it as close to what our general models need. Now, if we say what our general models need, it's usually like a table or a matrix. You know, I want to go from some unstructured data, I want to structure this towards my feature engineering, and so it's like a table or an Excel worksheet that kind of has my features if I'm doing a supervised type of learning. So again, we can feed it into the models that already exist. Then in our feature engineering, when we understand the data, we can start to see, all right, these are some of the features that I want to clean. I want to make it as pristine as possible, and I'm ready to feed it into our models. Sometimes in our feature engineering, we might also delete a lot of the data that we've received because too much data can actually contaminate some of your models. So we want to be as clean as possible before we get into modeling. And now finally, when we're at our modeling step, this is where we have our data, it's organized, it's as clean as possible, we're starting to feed it into our models to help us make decisions. Now if we say, whenever we do this type of, like people discuss artificial intelligence, machine learning, it seems like it's a sexy thing to do. I'm like my models are learning stuff. This is actually the most boring of the process. 80% of our time is spent converting our data in order to get it into modeling. Because really, once I send it into the models, I actually just have to wait. Sometimes you might have to wait 20 minutes. Sometimes you might have to wait 20 hours in order for our models to learn from the specific features towards making predictions. Then, after our models have made predictions, we go into our evaluation. And so the general terms that we use in evaluation is an objective function or a loss function. Did I put it loss function? No. Okay, so a loss function or an evaluation score. So if I have multiple models that I'm using to make a prediction or decisions for us, we now need to evaluate how well do those models perform. And so that's what this evaluation score will give us. Well, it has the smallest loss to the ground truth that we've analyzed before. Generally, the one that performs the best is the ones that we will use in our production environment. Then after we do that, we go towards our model selection. We select the model or multiple models that are as close to the historical data that we've analyzed, and now we move into our production. So our calibration, sometimes we may have to actually go back and make sure our models are correct, or we may have to adjust some things just to fine-tune the model when we're ready to deploy it. And then we deploy, we look at it, we do maintenance, and then you start the process all over again. Okay, now, If we've understand the foundation in the background, let's get closer to actually analyzing our malicious samples. And I'm looking for a timer. I don't know how much time do I have left? Yali, normally over here. How much, did you get a timer? Timer started? No? I'm sorry, what was that? 30 minutes? OK, all right, good. Yes, so we are, all right, we're good on time. All right, so now let's, as I said, we're moving into our multinomial classification. And this is where we could have multiple classes that we now want to analyze and say, OK, given an instance, which specific malware family might it belong to? Okay. So to start with, if we look at a PE, like a portable executable, a Windows binary, the Windows binary structure is rich with features that we can analyze. We can extract these features. We can understand, OK, the same, like as I mentioned, size, like import address header, the actual object code, the way the code is written, all of these are features that we can standardize. So we can extract these features. We can standardize it. As I mentioned, we go through our workflow. Then we can feed it into our models to determine, OK, what specific family might this malware belong to, or different characteristics about the malware. In reverse engineering, generally whenever I have a sample that I'm analyzing, I pretty much look at these 6 main areas to help me know what is that sample doing. So the first one is like the metadata. So like as I've said the metadata a few times, we can also look at the functions hash or fuzzy hashing. Just what is the composition of the sample itself? Well, those are features that we can add into our model. Another one is library functions. The library functions, if we can extract the library function statically, we can use those in order to infer potential operations or capabilities of that malicious sample. These are features. If we look towards its system calls, as we get lower level between the actual binary and the kernel or the operating system calls, we can also use those to describe a binary. If we look at these, if you look at many binaries of a similar family, you will generally start to see similar patterns. So what we want to do is extract these patterns and now put it into our modeling to help us detect these in the future. Then we can get into deep inspection of the actual binary in which we're looking at its functions, its composition. So we can use another type of artificial intelligence like natural language processing in order to start you can use natural language processing like for speech. How do we talk? Which sentiment is similar in what people say? Binaries have the same thing. There are strings, there are words inside binary. Its actual code follows a structure. So we can understand that structure. Again, we can start to cluster and see the associations and the similarities between different malware samples. I mentioned strings before, and then event tracing. We can now, besides looking at the sample statically, we can execute the sample and look at what overall does it do when it's running within a specific time window. And then if you do these time and time again, you again start to see patterns of what specific malware do. Generally, once it's instantiated, it's running, it's operating on the system. Well, what all does it do? Does it look to enumerate the hard drive? Does it now call some cryptographic functions? Do you then see files that were enumerated before? It goes through a cryptographic function. A new file is written, and then the old files are deleted. This is a common paradigm of like your ransomware. So if we can understand these traits and how it executes, as I said, we can use these as features to feed into our model. Now, I want to leave just with this quick reference. And so when we go into the modeling, so we understand features. Now we look at, OK, well, which specific model or what model types should we use? I would like to reference this entire book. And depending on how good your Google is, you can actually find the book in a PDF version. But this book it's like a Bible of many different research and analyses that people have done in various areas. And so I'm working on many of these, and so that book, like at least if we can see what people have done before, it makes it easier for us to apply this into our own specific domain. Okay, now let's look into our feature acquisition. So show of hands, VirusTotal, are we familiar with VirusTotal? Yeah, that's most of the room. Excellent, excellent. Okay, very good. So if you have used VirusTotal, here we have a sample that we've submitted to VirusTotal to determine is that sample malicious. The first thing I'll always look at when I submit a malicious sample to VirusTotal is how red is it? The number of detections that we have given the number of antiviruses that are plugged into VirusTotal at that time. And so here we see like for this specific instance, I can't remember the type of binary that I used, but 60 out of the 69 AV vendors, 57 of them said that sample is malicious. So yeah, we can pretty much conclude this sample is malicious. Okay, very good. Now, if we look down towards the data that VirusTotal provides, these, like the metadata, descriptions of the binary sample, that's metadata that we can use into features. Looking at the library functions as potential capabilities and the way that malware can operate on the system, library functions, these are features. And then the same thing on this side, like its behavior. So I'm not sure if VirusTotal actually did a deep inspection of code, because I do that as well. But at least they can give us a summary, even attaching this to MITRE ATT&CK framework to say, these are similar things that we've seen in this specific sample. Those two are features. Okay, good. So now you're already familiar with looking at features. Here is the problem with using a tool like VirusTotal for your feature extraction. Well, access to large, commercially available data is generally expensive. And so how expensive do we mean? In our lab, we have terabytes of malware. So terabytes of malware, that's thousands and thousands of unique malware samples. I reached out to VirusTotal to say, hey, I really just want your antivirus detection so I can kind of just use this as ground truth. Can we partner? Like, what does it look like if I submit your samples and then I can just automate the process, so I can go back into our artificial modeling? VirusTotal comes back and says, access to our data costs hundreds of thousands of dollars. Hundreds of thousands. Like, I don't have yet hundreds of thousands of dollars to submit just because I want to see your ground truth samples of malware according to the corpus that I have. So when you don't have an easy way of extracting your features from another created repository, then it just means we need to create that analysis ourselves. And so here's what that analysis pipeline looks like. We start with a malware corpora, multiple corpus that we have. And yeah, I think in one of our next slides, I actually list the different really good repositories for getting just large samples of malware. So for each malware that we have from our corpus, we now want to analyze this and automate our process. So we want to write an agent that helps us to extract like the metadata, the features that we spoke about before. Then when we know the features that we want to look at, we do have to do some sort of normalization and reconciliation. Like compilers might use different forms of optimization whenever it's compiling its code. So we kind of need to reconcile how some of our features are extracted just to make sure it's as normal or standardized as possible. And then we get into our knowledge-based translation. And I'll explain this a bit more in the oncoming slides. But at least starting from an executable, we can abstract the features that we need into our specific areas that we spoke about previously. And then this is ready to be fed into already existing machine learning models. So if we can do that, then now we can already feed a brand new sample I've never seen before to start to say, models, do we think it's malicious, yes or no? Or if we do think it's malicious, what specific malware family might it belong to? Or perhaps we can establish code prevalence, in which we're seeing like these code has been shared between different malware samples just to help us detect things that we've never seen before. This is generally what that pipeline can look like. All right, so on the previous slide, you did see like there was a red square in terms of like how do we get closer to creating our features, all right? Let's go a bit further. So as I mentioned, these are really good sites for malware repositories. VX Underground is my favorite, as well as Malware Bazaar. You can just download their entire repository, get gigs and gigs, and end up with terabytes of malware. So again, for each sample, we can now write an agent. And so our agent is our binary analysis orchestrator that's going to analyze each sample. And then on Remnux, I wrote the agent on top of Remnux. Remnux is an incredible reverse engineering malware analysis distro that has many tools already created and populated in this distro. So we can learn how to use these tools, that we can use an agent to automate those tools and then provide us specific amounts of data. Now here, I put my favorite specific tools used by our agent in order to help us analyze the sample, such that if you wanted to go off and to be able to recreate this entire process, these are all of the tools we want to show you as much as possible. Then, as our agent is analyzing or launching all these various tools, they're going to give us data in disparate formats. So then we just want to take a step back and understand, what am I looking at? So we can go from these specific tools to give us like this type of data, like our metadata that we want, our sections and our features. Disassembly, these are really good tools that you can automate. And then, just moving down, we want strings, we want signatures, compilation data. These are the tools to help us kind of summarize the details that we're extracting from a malware sample. And then when we have those features extracted, we now introduce another agent called our file descriptor that helps us look at the data that's extracted. It puts into our knowledge base. And then we take data from our knowledge base to translate it into a matrix. And so if we can translate our data from an executable over to a tabular form, then we're ready here to pivot into our machine learning pipeline that we spoke about before, and then our final deployment with a classification agent in between. All right, let me try and help show that one more time, just one more quick dive. So here we're using two tools from our agent. So Manalize is a great tool on the Remnux distro. It can just give us lots of metadata about an artifact, like for instance, its DOS header, PE header, its image, optional header. All of these, as I mentioned, we can standardize the same artifact from different samples. We can use these as features to feed into our models. And we can do the same thing even with the composition of the disassembly. So when we take that, hopefully this makes sense now of going from that sample, the corpus, binary, orchestrators, into creating our table. And then once we have our table, you're now ready to immediately feed these into various models for classification and analysis. We've also looked through every is that's a loaded word, but all of the malware associated to a specific malware family from VX Underground that we spoke about on one of our previous slides. We analyzed that, and then we've actually released that data set to the community. And then if you like, you can go to our GitHub here under the National Science Foundation to extract the data set. And so this data set you can immediately pivot into different types of learning. And then also towards the end, I'll talk about the GitHub in which I will be uploading the notebooks that you can do this directly. So I want it to be as quick, as click-friendly for you, and I'll try and annotate things as best as possible. So again, you're ready and you're able at least to start playing around with these models to learn more. Wait. Yep, and I just spoke about that. That will be on GitHub. Okay, now I want to also apply image casting on convolutional neural networks. I want to talk about that real quick, but I don't know how much time we have left. Sorry. So I usually started. I just missed starting the time. How much time is left? I'm sorry? 10 minutes? 18. Okay. Okay. All right. Good. All right. We're progressing well. All right. So let's talk about this. On this slide, so a convolutional neural network. I think if we've heard the terms artificial intelligence, machine learning, CNN, convolutional neural networks is one of those artificial neural networks that has been mentioned. Like we use this really, really well. It works really nicely. So the normal domain for a convolutional neural network is kind of like for image classification and textures as well as edge detection. So here we are. We have this type of deep learning neural network that we can use to classify different types of images. And then the general input is like an image, a video, or even audio data types. Facebook, or let's just use Facebook for instance. Have you noticed that on times when you're on Facebook, you upload a picture, and then Facebook will say, hey, I think this is a friend from your picture. You're like, well, how did it do that? It's actually using convolutional neural networks in the background. So it's learning features from the image that is received, and then it looks at all of the images that it has before where people have tagged it. And then based on the similarities, it says, I think this image that you've given me is this person. Sometimes it's way off. It can say it's a statue. It can say it's something random. Or other times it's actually close. And the longer and longer we have data that's uploaded to things like Facebook or other social networking sites, the more precise it's going to be. But that's what's working in the background, large convolutional type of neural networks. All right, let's get a bit further. So I have another example here that I'm just showing where we start from an image. So over here can be like a car or a vehicle. Inside a convolutional neural network, there are multiple setups that we use for that convolutional neural network. So we start with an input layer. And so the input layer is the image. So if I have a picture that I'm sending into our convolutional neural network, that image is generally multidimensional. And so that image has a height, a weight, and then there could be multiple channels for each color. like your RGB, red, green, blue, the color that composes the image, we can actually extract those, but each one is a specific dimension. Then we go into our convolutional layers, our hidden layers in which we convolve the image. So convolving the image, this means I have a filter of a specific size, and then I'm analyzing, I'm scanning the image to understand like what are the unique things that reach out to us. The more individual layers that I have, or perhaps another example is if I have a straw, I can only look through a straw. So if I have my entire image and I have a straw, I can look there at a specific time. My convolutional neural layer lets me see at a specific width or window that I'm looking at, what are the features there. So as I scan the entire image with multiple layers, I'm now starting to see, okay, here are the unique features that are sticking out at each window size. Then, from our convolutional layers, these are usually attached as soon as you do a convolution of the image. I'm just filtering, looking for specific features. We then have an activation function that's associated to that window. So the activation function, it allows us to introduce nonlinearity in order for us to determine or figure out more complex images or more complex features from a window that we're looking at. Okay, then from that aspect, we now have pooling layers. So each time we do our convolution, we're now getting still more and more layers. So our pooling layer kind of helps us flatten the image or flatten those layers to make it more simple again. It also helps us reduce this term overfitting. I should have written it in here somewhere. Overfitting. So overfitting, this is when our models, they learn too much from our training data, but then when I give it data it's never seen before, and our test set is not able to generalize well. So if I have a really granular or pixelated image, I can send this into our convolutional neural layer, but the specific, the distortions in an image, we don't use a distortion if someone was running and you take a quick picture, it could be blurred in the background. But we don't use the blurring pixels as a classification mechanism. You want to look at the colors that are specific. So that's why we have our pooling layers that helps us simplify that. So again, our convolutional neural layers, our network here, it throws away some of the distortions so we can simplify the image. Then when all of that is done, we have many layers in between here. We start to go towards our fully connected layers. So our fully connected layers, this is where you would generally have your multiple dimensions down to 2 dimensions, and then we want to go from our 2 dimensions, again, we're simplifying this, to 1 specific dimension. And so the word flatten, flatten, right here. And so as I mentioned, if you start with a multiple dimension image, I now just want a single 1-dimension feature vector, a really large feature vector that says these are the unique features that we're able to identify for each object that's going in. Now we can use those specific detections. There's light, there's an edge, there's the dimensions of where one eye is from the other. We can use these to help us identify similarities in other images that are going through. Okay, so that's just the general domain of a convolutional neural network. So how do we apply this to malware? All right. So it's right here. So I still find this very, 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 very fascinating. So we can take a binary, a malware sample, a Zeus bot, Dooku, Flame, etc. We can take that same executable and cast it to an image. So that means the bits that represents the image, I can now use that to create some grayscaled image here. And so this is what we have, 1, 2, 3, 4, 5. These are 5 unique variants that belong to the Zeus bot family. When we cast these into an image, it's just zeros and ones, grayscale, because we want to have as few channels as possible. This is what some of those samples actually look like. I still find this even as I'm talking about this, and I did it, it's still interesting. But if you look at these, even with our own eyes, you can see similarities. So that means if you can see similarities within various samples, then we can use a convolutional neural network also to find the similarities of those same samples, but at a more fine tune than what our eye can ever see. So if we can do that, then we can build our entire model to recognize the textures from previous samples, and then we can also add this as a selection or a classification mechanism to detect new malware of specific variants that belong to specific families in the future. Okay, I want to introduce you to deep image search. So deep image search, this is a framework that has multiple convolutional neural networks built in. And so as I mentioned, I want this to be as applicable as possible. So on your environment, you can search, you can Google, what is deep image search? And then you can figure out, or you can see kind of how can I use different models within this framework. So here I'm just saying it's a Python library, uses deep learning for image retrieval and similarity searching. So we can use this as a framework of many other models together, kind of in a unified manner to do our malware classification and detection in the future. Now, in the slides, I'll be sending the slides like right after the talk or so. I actually go through how you can start to finish to take malicious samples, cast them to images. Like this is really the code to take a malicious sample here and then cast it into a specific image, and then we start loading it through that entire the entire framework. And so also on GitHub, I'm putting this up. So the images that we're starting with here, it's just called grayscale, and then that's the password infected. So at least I can put it onto GitHub or Google Drive, and then you can download it without like the malware proliferation error alerts that I usually get from these sites. So to start with, we'll look at 23 unique families that are inside this set that you can download. Within the family, we have between 4 and 7 unique samples per family. Altogether, we'll have 154 images that we want to identify and classify. Now, in the slides, as I mentioned, I have exactly how you set it up, but I want to go to the end because, I mean, what's the point of looking at code? You can do that, on your own. But I'm just saying, I try to tell you how you can set this up. But let's go towards the useful aspect of it. So the useful aspect is here. Okay. So after we load this package, deep image search, you can specify which specific convolutional neural networks that you would like. Then inside the code, I made it as click and play friendly as possible. You send your images through the different convolutional neural networks, and then it will give you a classification. And so as we do this more and more, we will start to see how do we evaluate which model is better. Each model here, these are the model names, and I just used a few just because it's going to take some time to train. But each model, they are able to find or identify image features specifically in the data set. That's why we use multiple ones to say, okay, which is the best? Different classes or different malware variants have different ways of, they have different features, but different models are able to identify these features differently. And so here we want to look at the best model for that specific class, and then we incorporate this into our classification. Okay. Now, I'll move forward. So here's something also that we're able to do with this. So we're able to give it a specific malware image, like that Zeus here. I'm just saying it's at index 109. And then we can say entire framework, give me the images, give me the malware that are similar to the one that we just said. And so it can also give you those images. And then, as I mentioned, it's really nice being able to see that, yes, this does a pretty decent job at identifying the similarity in malware. So we can also use this for code similarity and classification moving forward. Okay. Now we'll go towards kind of the overall summary, and then I think we'll be done. Can you give me a time real quick? About 7. Okay, good. Okay, so here, when we do multiple models, so you don't have to worry too much about the words here. Just know that each line represents a specific model. And then on this side, we're trying to say how well that model performed in the classification of images that were fed to it. So generally, whenever we do this, we use multiple models to make a decision. We look at the evaluation of how each model did, and then you select the best model, and now you use that towards your operation. We already spoke through that about the classification, then our workflow at the very beginning. But I want to say that, yes, we can get models that are quite good. Just know, this is a number. It's, this is the best model from our entire framework that we're using, but we can actually be better. And so this is why I'm talking about the concept of the heterogeneous ensembling, or a heterogeneous ensemble learning. So anytime we talk about an ensemble, it just means I'm taking multiple models, we call them weaker learners if they're not specific, to do a really good job. But I can take weak learners, I can aggregate their classifications together to develop a strong classification mechanism. And so that's the whole purpose of creating that heterogeneous ensemble. So here, this is very similar to the previous slide that I mentioned before. These are different models that we have. Now we're using more models on the data set that we've released, and we said it's, it's part of the National Science Foundation, Mabel data set. You can already take those. You can use the workflow that we'll upload onto GitHub, and then you'll be able to recreate this process. So here we're seeing how each model performed, and then this is the overall evaluation score for each model. And at the top, your general process is we look at multiple models, you select the best model, you move those forward, but we can be better. And so I'm showing here that if we know how to pry inside the performance of each model, we can now use the entire model space to help us identify what is the best classification moving forward. So again, instead of looking at one model, this is usually the best overall model, but if we talk about a specific class, that best model is not always good in each class. That's why we spend time to analyze how well does each class perform, and then you select the best mechanism from those classes, and then you move forward. The literature, you'll generally see this referred to as voting or stacking. And so here, we're just trying to say that voting or stacking, that is a really, really good approach, but it's not always one or the other. There are times you have to blend those approaches in order to give us the best detection mechanism. So I'm just going to show quick results that here, just again, these are words. These are different strategies that we've built in order to help ensemble different models together. And then inside these, we have that agent, our classification arbiter, that we have to program in prime directives of how it makes decisions in order to look through the models. So you have artificial intelligence that's looking through your data, it's making decisions, and then you have a separate agent that has directives on how to look at the models, on how we go towards our classification. And then as we've created our heterogeneous model, we are already starting to see the better impacts with our ensembling than from previous. So there is utility in being able to apply artificial intelligence towards detecting what we know and things we've not seen before moving forward. Okay, so now we're going towards the summary. As I mentioned, the code will be uploaded towards GitHub. I think I should, depending on how tired I am when I leave here, I should be posting the link hopefully in a few hours or by Monday or Tuesday when I make it back home. Yes, yeah, and then the last thing. So I remember my journey when I got started into artificial intelligence, and the spoiler alert is it's a never-ending journey. But for people that are interested in how do we get started, what are some of the things to do? Okay, no problem. Well, I put kind of the best resources that I found that I think is pretty, standalone, that if you start in reading one, you can already start to implement this type of modeling and detection in order to have artificial intelligence into your respective domains. And so there is a little knowledge that's needed. We do need to know a little bit of math, at least to evaluate our models. We do need just a little bit of programming, but there's so many resources to help us with how do we just use Python in order to help with our machine learning process. And then there's education I mentioned. Some are you might have a week-long boot camp that's boot camp for artificial intelligence. A week is too short. But at least take some time, and as I said, it's a never-ending process. But some of these resources are really, to me, they're really good. And then I think in the slide you can actually click on these and it'll take you to the Amazon, or depending on how well you can Google, you can find all of these online as a PDF. And so hopefully these just leaves resources to get started and then to better understand your artificial intelligence in your domains. Okay, that is it for now. I don't know if I have time for questions, but are there any questions? Thanks.
Thank you very much. We are going to do a recorded Q&A with you afterwards. Now we're taking a 15-minute break before the next.